the recording and share my screen and jump into the notes here. Right. So I guess I'll start with general comments on the exam and preparing for it. So the exam is 12 questions this time. And how in the past I've done it is there are some that are conceptual, some that are more calculation based. And the conceptual ones are multiple choice. So you will have some options, you pick one, whether you get the credit or you don't, just depends on circling the right answer. And those are on this exam weighted at 6 points apiece. So they are kind of all or none, 0 points or 6, whether you get it wrong or right. So it's important to look over the concept stuff for that. You can use the practice, adaptive practice, and pre-lecture videos on Wiley for that. That helps with concepts. The rest of the questions, the other 7, are calculation-based. They are not multiple choice. There are no options. It's just calculate, find the right answer, and put that down. They're weighted at different point values depending on how difficult the question is and how much work it takes. So how it goes is the more work it takes, the more points it's worth. The more difficult it is, I would scale back the points a little bit so that it's not going to hurt you as badly if you're not able to get it right. But sometimes those don't balance out perfectly. And also with how short the exam is, just to make sure you have time to do the questions. Some are weighted pretty heavy. So the most is 12 points for certain questions. And the front page is exactly like what is in the review. So you may or may not have looked at these practice questions yet, but this front page, it looks exactly the same on the exam. So read over it, notice what equations are there, and use that to inform what you would want to put on your equation sheet or cheat sheet. It can be the front of a piece of paper, regular piece of paper, whatever you want to put on it, and you just have to turn it in with your exam so that I know what you brought with you. But 9 times out of 10, 99 times out of 100, I'm usually fine with whatever you want to put on it. And I think that's the big sort of ground rules for the exam. Are there any questions before we start reviewing the actual notes? Okay. So I will go ahead and jump in then, and I am looking at the exam as we go through this to kind of help you know what you want to look at. So something here, is there any way, what's a homework problem? Yeah, happy to do that at the end of the review. We can go over whatever. All right, so we are, yes, that would help, Haley, if you can do the timestamps again once that's up. I would appreciate that. All right, so jumping into it, chapter 18. Of course, the first thing is that some things attract, some things repel when you put them near each other. And it is important to realize that that is due to this movement of electrons. In all of the cases we've talked about of things becoming electrically attracted or repelling each other, it's due to the motion of electrons, not positive charge. How you get a positive charge is that electrons leave that thing. And so there's less electrons than there are protons. And then they move on to something that then has more electrons than protons. They become negatively charged. So the fact that this sort of charging happens due to electrons moving from one thing to another. And then we've seen that you can have charging by direct contact. So friction charging is an example of that with insulators, but with conductors, it's even easier. It's just you touch the charged object to a neutral conductor, and some of that charge is deposited onto the conductor because it really likes to become charged, move charge through it. There is also induction, and in that case, you are bringing a charged object close to, but not touching the conductor. And that tends to create this separation or polarization of charge, even on neutral conductors. So in the case of negative charge being brought close, that repels the electrons here, leaving a net positive charge on this surface. And as soon as you take that rod away, that separation of charge will go away. It'll become neutral again here, unless you give a way for some of that charge to seep off the conductor. That could be touching it with a wire directly to ground, or like you've seen me do in class, I'll touch it with my hand, some of that charge moves onto me, and you can leave a net positive or negative charge on that conductor by doing that. So induction's the weird one in that you can still see these electrical forces happen with something that was originally neutral. And that's an important thing to realize, is that you can have things that they have zero net charge, but because of something charged being brought close to them, they become polarized, and then you still have that attraction or repulsion happening, which, by the way, you may have done in lab. Very first day, we said, wool and PVC, if you rub them together, they will attract each other. And ideally, it would be the case that if you did that with 2 sets of PVC pipes, 2 sets of wool scraps, the PVC would repel the other PVC pipe. But that actually is not what happens. And I think in your lab, you do something similar to that. So does anyone know why it would be that the 2 don't actually repel, and what happens instead? And this was something that it took me a while to realize. I was trying to get it to work for like an hour, trying all these different things, thinking, I wonder why this isn't working. And then I realized what it was. So it's not immediately obvious. Two things to think about. Induction and humidity. So what does humidity tend to do to charged objects? And why it's been so unfortunate how humid it's been lately as far as our class goes. It's okay to be wrong. Now's the time for wrong answers. Yes, it neutralizes the charge on objects because water is slightly ionized, some slightly positive, some slightly negative, and you end up having the opposite charge attracted to the charged object like the PVC pipe, and you lose a lot of that charge quickly. And so what ends up happening is you rub the wool on both the PVC pipes, you set one down to try and get the other one charged. And by the time you've done that, the first one may have already become neutral. And so when you bring the other one close to it, what will happen is it induces charge in the one you had set down and attracts it instead of repelling it. And I sat on that for a while and thought, why is this happening? Why isn't this working? And that's why we didn't do it in class, because most days it would end up doing that instead of the ideal repelling that would happen if we just had the net negative charge on both. So that's where things can get a little confusing with induction. Anyway, Coulomb's law is very much on this exam. So it is that it's a quantitative statement of things attract or repel depending on if they have opposite charges or like charges. And it tells you exactly how strong that force of attraction or repulsion is. It's Coulomb's constant times the magnitude of the charge for each charge involved. This only applies to point charges, but that's really all we've looked at for most of the class so far. And the distance between them. And so the kind of questions you might expect to see on the exam for this are ones like these two down here of finding the net force on something using Coulomb's law. And you have just this picture of an arrangement of charges and you're asked to find that net force and maybe even remember Newton's second law, other laws about how that force relates to acceleration and things like that. So these are good ones to look at. What else we got? Electric field. So the idea of the electric field is taking a step back from electric forces and wondering what leads to electric forces. We say it's that every charged object sets up an electric field in the entire space around it. When you put other things that have charge in that field, then the interaction of the two fields is what creates these electric forces. So the field is the more fundamental concept, but we define it in terms of that force because we use this concept of a test charge to say, if I put a charge in this field, how much force is felt by it? So remembering how electric fields are defined is going to be important in some problems. This is the most general way of defining writing the electric field. There are specific cases we've seen, like for the case of point charges, that's where you have the KQ over R squared for the electric field. But this, that is the force felt by something over the charge of that something, is the most fundamental definition of the electric field. And then knowing that electric fields add like vectors. So you can find the net electric field using your regular old vector math is important. You just need to remember which way that field points for different charges. It points away for positive charges, towards for negative. So ones like this that are a little more quantitative are good, as are ones like this, just knowing the direction of the field. You may even want to look back at some of the homework on electric fields and finding the net electric field, because that will likely help you. Field lines. The important things about field lines are they are describing in a more visual way the electric field by basically taking the electric field, plotting the vector at a lot of different points and connecting those vectors with these lines that are tangent to them. And that gives us a better sense of the idea that positive charges tend to be repelled away from other positive charges and attracted towards negative. That's why the field lines point the way they do. They're defined in terms of positive charges, just like the electric field is. So it's good to know which is which, as far as you have some field lines pointing away from one thing towards another, and then just how field lines are drawn, kind of your rules for them. So if this example here makes sense, why 3 of them are correct and 1 of them is not, then I think you're pretty good to go on field lines. Capacitors. So what's unique about the electric field for a capacitor? straight across. And so in terms of field lines, if they're all straight across, evenly spaced, yeah, besides the edges, besides those fringe fields, what can we say about the strength of the electric field? It does curve on the outside, so that's the fringing. We usually ignore that in most of what we're talking about, but it does happen. So think about dead in the middle of the capacity. Yes, it's equally strong anywhere between the two plates, and that's because of these components canceling in all directions but straight across, and that you have this kind of equal distribution of charge on the surface of both plates. That makes the electric field itself between the plates uniform. It's what we call it. Same direction, same strength everywhere between the plates, except the fringing, which we kind of ignore because it gets too complicated to look into too much. But the important bit, electric field there is uniform. And we've realized now that you don't actually want charge in between your plates as far as moving from one to the other, because that neutralizes some of the charge on the plates. But you could, in principle, have that and look at what's happening to a charge between the plates. Knowing what direction the force is on it, it's in the direction of the field for positive charges, opposite that direction for negative. And the fact that that results in an electric force on the charge is important. And again, remembering Newton's laws, how those kind of work. So your physics 1 stuff. So maybe just read over that little blurb there. Gauss's law for us was more of a tool. The higher up you go, deeper into physics you go, you do use it more as what you're actually solving problems with. But for us, it was sort of a means to an end. So I'm not concerned so much about you calculating flux, but it is important to know the results of Gauss's law, which say that, for instance, for a charged sphere, the electric field looks like that. It looks like a point charge from the outside. There's zero field inside. And that is related to what we learned about conductors having no electric field within. It's because that charge likes to distribute itself over the surface of the conductor. If we look at this example, we were saying it is a sphere with charge uniformly distributed over its surface. So that's exactly what would happen for a conducting sphere. And we got to the capacitor. The electric field for the capacitor is the charge on either plate divided by the plate area, and that epsilon naught, which we now know tells us something about how well charge can be separated, polarized in vacuum, and then our dielectric constant tells us relative to that how well it can happen in other materials. Okay, so this is on the equation sheet, but knowing what it says is probably a good idea. What else we got here? Properties of conductors. It may help to read over them just to kind of remember what it is that conductors do, how charge moves on them, but it's not a strong focus on the exam. So you may have things where there are conductors involved in a problem, but it's not asking you to leverage too much this knowledge about conductors to solve the problem. Okay, so that's 18. 19, we started talking about potential energy. So the first big thing was that we can relate the work done on a charge moving between 2 points in an electric field to the change in its potential energy, and then we divide by the charge of that charge moving through the electric field to get something that's independent of it, a lot like we did to get the idea of electric fields. The difference is electric potential is a scalar quantity. It's the potential energy per unit of charge. And so it is, in some sense, a energy density, energy per coulomb of charge. So you want to know how it relates to the work done on a charge. And so that's this work is negative Q VB minus VA. I think we write it like that, yeah, down here. So this would be final minus initial still. This is not that high minus low thing we're doing now with voltage. This is always final minus initial if you see delta V. And let's see. Knowing that at the end of the day, electric potential is a way of figuring out changes in potential energy, because that's a sort of physical thing that's happening to these charges is their energy is changing, and that can be useful in these conservation problems. So it's good to know how potential relates to the work done, but also the fact that electric potential energy is just the charge that's moving through that electric field times the potential difference it moved through. Right. This is just good to clear up in your head the difference between these four things. Electric field, force are vectors, potential energy are scalars, but the field and the potential are these per unit charge concepts. We're saying they exist whether we put another charge there or not. Any charged object creates an electric field, creates an electric potential at every point in space. If you put another charge at one of those points, it experiences an electric force. It gains electric potential energy. So we figured out the potential for a point charge. It's KQ over R, or I guess we had that right here. That is important on here, knowing the electric potential for a point charge and possibly multiple point charges. So examples like this one are a good idea to look at. And knowing that depending on if you have positive or negative charge, that changes the sign of your potential. There could be one like you've got an arrangement of charges, you bring in one more, what happens to its potential energy? So it's just find the potential at the point it's moving to. If it's moving in from infinity, it started with 0 potential energy. And so you multiply that charge by the potential at the point it's moving to. So that would be like this last one, bring in Q3 when we've already got our other two charges there. Equipotentials are on this. So it is important to know their properties, the relationship between work done and change in potential that we already talked about, as well as the relation between the electric field and the electric potential. So which way does the electric field point in terms of the potential? High to low. So positive charge moves from high to low electric potential. Field lines point away from positive charge. Those are not a coincidence that both of those work like that. It's because we've defined everything in terms of positive charges. So we have a positive charge, sets up an electric field pointing away from it. That's going to repel another positive charge. And so it moves from higher to lower potential. So that's the relationship between them. If you know something about the change in electric potential, you know something about the electric field, both direction and magnitude. The magnitude part is what we did here, the relationship between electric field and change in potential. And capacitors are the last thing we looked at for this exam. And it's important to know how to calculate capacitance for parallel plates. This is not how capacitance is determined. So that's what we found out from the quiz today, or going over it, is that these things are related, but like with the water tower, how much water is in there and what height it goes up to are determined by the water tower's geometry. Just like how much charge are on these plates and the potential difference across them is determined by the capacitance of the plates, not the other way around. If I quadruple the amount of water in this tower, it doesn't get larger. Just like if I quadruple the charge on these plates, they don't get larger. You just have more charge on them. What does get larger is the height of the water in the tower or the potential difference across the plates. So capacitance is independent of charge and voltage. It just relates the two. What it's determined by is the dielectric between. So understanding what dielectrics do is important. And just at the end of the day, what capacitance is for parallel plates. It depends on the plate area, plate separation, and the dielectric material in between. So let's see. What we have here. So there can be conceptual ones like we talked about more with energy, but this still applies if you're just saying how much charge is on there, if I change the potential difference, or if I change the capacitance. So it's that thing of if I keep the charge fixed, but I increase the capacitance, what must happen to the potential difference across the plates? Or if I keep the potential difference fixed by using a battery or something, and I change the capacitance, what happens to the charge on the plates? So that's again saying the capacitance is not determined by changes in these other two things. It determines how they change. And so there could be questions like that, not so much on calculating potential energy, but just using these ideas that we came to explain why we saw that potential energy could increase or decrease with changes in capacitance. All right, I think that is everything. So this example is a good one for the calculation, and then this is a good one for conceptual. All right, that gets to the end of the exam. And there is one bonus question on there. It is a Gabby question. It took me a long time to come up with one related to electricity stuff, but I've got one. And so that one is 6 points. It is not multiple choice. It actually requires you to write something down. Think of it as like a short 1 or 2 sentence response type question. But that is the review. So with that, whatever questions we have, whatever we want to look at, I am ready to go over. Other questions? Page 8. On this or on the review questions, practice questions? Okay. Because remember, there is those practice questions. So I'll just pick some to go over, or if there's specific ones you've already tried, which I hope you've looked at least for 5 minutes somewhere. We'll do that. All right. The direction of the force for each charge in the box at the bottom. So remember that field is a property of a charge. And so what we're saying in this picture is that I've got this charge here. It produces an electric field. Forces only mean anything if there's another charge that I put somewhere in this field. And so if I put another charge in the electric field of this one, say a positive charge, it would be repelled. So it would be in the same direction as the electric field. If I had a negative charge, it would be attracted, so opposite the direction of the field. Also, it is the case that this charge will exert a force on the other one so that it is repelled if that charge is positive, or attracted if this charge is negative. And that's because of this charge's own electric field. But we usually try and keep things simple and just say there's one really large charge, a lot of mass to it compared to one smaller one. So the only one that really moves too much is the smaller one. Same with negative charge. We put a positive one here. It will be attracted towards it in the same direction as the field. If we put a negative there, it will be repelled opposite the direction of the field. So positive charges always experience forces in the direction of the field. Negative always experience them opposite that direction. Does that clear that up? Yep. Okay, good. All right, other questions? Number 9 on the practice problems. Okay, so got a parallel plate capacitor. We're given something about surface charge density. And we've got this point 1 times 10 to the negative 5 meters away from that positive plate. What is the magnitude of the electric field at point P? Now, this one is a little bit tricky in that, does the distance of this charge from either plate matter? As far as determining the electric field? No, why doesn't it? Because not exactly just parallel, but again, uniform. So I guess in terms of field lines, if they're parallel, that means that the field is uniform, but it's the strength of the electric field is exactly the same everywhere in between these two plates. So it doesn't matter whether this charge is here or down here, somewhere else up here. It's still going to be the same electric field at any of those points. Now, if we're talking about the force on a charge, that depends on the charge that we put at one of those points. If we're talking about the electric potential at different points, then that does matter where we are. So if we still call this V, our potential difference high minus low, halfway between the potential difference between that and the negative plate is V over 2. A quarter of the way, it's just V over 4, and so on. So it does, plate spacing does matter for some things, but not the field. And that's because the electric field between the plates of a capacitor only depends on the charge on either plate, that constant epsilon naught, and the plate surface area. Or we can write this as the charge per area. So think of like coulombs per square meter of this surface. We usually write that as sigma. So that's this Q over A. And that's what we're given here, coulombs per square meter. So really all we need for this is that right there. And it's 8.8 into negative 8 coulombs per square meter, 8.85 times 10 to negative 12 coulomb squared per Newton meter squared, if I remember right, for epsilon naught. And we can check our units, coulomb per meter squared, divided by this, you're multiplying by reciprocal. You get Newtons per Coulomb, which is the units of electric field. So doing some mental math here, I think that's a 10 to the 4 minus negative 12. So something like 1 times 10 to the 4. That 5 makes it a little bit not quite right, but something along those lines. And I can open up the this one, see if I'm close. Yeah, so 1, it's almost 1 times 10 to the 4, because if it were 10, that'd be 10 times 1,000, which is 10,000, or 1 times 10 to the 4. So that should be that one. Okay. I should put my units there. All right. Does that clear that one up? Yep. All right. Other questions? Other ones we want to go over? Number 12 on the homework. So for the moment, I'm going to wait on that because I'm happy to give tips. And I'll do that at the tail end of this. But as far as completely going through it, I can't do that. So let me see. What was that question about? Because it would take me a minute to try and pull that up. Okay, so yeah, what was that one on? And I can maybe at least give some advice, a pointer on it. Work done by the electric charge or electric force as the test charge moves from one surface to another. You know what? Let me just pull it up real quick on other computer here, because I don't remember the exact one. While I'm doing this, other people will be looking at other problems you want to look at, so we can keep things moving. That keyboard is deafening. So sorry for that. Rounded, which has a radius of another work done is that. So find that radius. Okay. So we've got this positive charge. It's got equipotential surfaces at different distances. And since it is just a point charge, its equipotential surfaces are just spheres around it. So we can describe them by that radius. We've got another charge moving from that radius to another one. And the question first is whether that radius is larger or smaller. And so the work done on the positive charge as it moves from A to B is a negative number, 9.39 times 10 to the negative 9 joules. And so it would tend to decrease the speed because of that negative of that positive charge moving. That would happen if it's moving towards this other positive charge because it's feeling this repulsive force that's pushing back on it as it moves towards the positive charge in the middle here. So the first thing we would see is that the work done in moving from A to B means that it must be that B is closer, or this equipotential surface is closer to that. And then it's about realizing how that work relates to the potential at each of these distances, and then how we can write the electric potential for a point charge, which is what this is at the middle. And that should be enough information to let you find that distance RB. Does that help with that one? Yeah, so first step in any physics problem, or almost any, is a good picture. Sorry about that. So that is the hardest part too, is drawing a good picture that actually describes what it is you're reading. But it is the most important step because setting up the equations and things just follows from looking at your picture and seeing which ones apply to it. Okay, so other questions for these practice questions or anything else? Number 6. Okay, this one right here. So we've got 3 charges. What are horizontal and vertical components of the net force on this 15 microcoulomb charge due to these other 2? So first step with these types of problems is always determining whether this charge is attracted or repelled by the other charges. We've got that this is positive and this is positive, so it's going to be repelled. So that might be, if we call this 1, this 2, this 3, the force of 1 on 3 points that way, points up. The force of 2, since this is also positive, points away. So that's a force of 2 on 3. And we want to know the horizontal and vertical components of the net force. So putting these both together, what do we get? And it's going to help us to know then this angle, because we need to break this one into horizontal and vertical components. This one from the charge down here already points strictly vertically. It has no horizontal component, so that one's going to be pretty straightforward. But from this, we see that this angle must be 37 degrees as well. So we just go back to our usual, what is the net force in the X? What is the net force in the Y? Net force in the X is F23 cosine 37 degrees, cosine because we've got F23 that has horizontal and vertical components, X and Y. And so what's adjacent to our 37-degree angle is that horizontal component. So cosine 37 is the adjacent over hypotenuse, or that horizontal component is F23 cosine 37 up to the sign, SIGN. Because this points to the left, we're used to calling left the negative direction, so I would say that's negative F23 cosine 37. There is no vertical, or excuse me, no horizontal component from this other force, so that's it in the horizontal vertical. We have F23 sine 37, and it is upward for that component because the overall vector points to the left and up. So that's positive. And then we've got positive F13, the force from this charge. So all this can be done without ever using Coulomb's law. We've gotten to this point. Where we need it is to figure out what these force magnitudes are. So it's just, this one's K, Q1, which is my 13 microcoulomb. Q3 is this one up here. We've already accounted for direction, so I'm going to say that's the magnitude of those charges. Over our distance is 0.075 meters squared cosine 37. And then for this one, I'm going to wrap around here. This is KQ2 magnitude, Q3 over this other distance, which I guess we were not given that one, so we got to find that real quick. It's a right triangle. So this is a pretty dense one, but that would be our other two sides squared and added. And can someone put that in for me? Find what that distance is. So I'll just keep filling in while you're putting that in, because I'm going to put it right here. So then this is still just the, I messed up here. So this was our X, that's the cosine 37 one, so that is this distance. So that should be whatever we get here. 0.125, okay. So this one was the force on our charge up here due to this charge, and that's why we needed that cosine in the first place. So my mistake, that's Q2, Q3, and we just found out that that was 0.125 meters squared. And then this one also, Q2, Q3, 0.125 meters squared. And then this one, K, Q1, Q3 over this distance, which that's the one that's 0.075 meters squared. So if we put in our charge for 2 is 11 times 10 to the negative 6. For 3, it's 15 times 10 to the negative 6. And then for 1, 13 times 10 to the negative 6, we should get our components. So let's see. Y'all be trying that to see what components you get, and I will also put it in, see if we get the same thing. A lot of room for error in this one, so hope I was careful. Anyone else starting to get some numbers for this? I'm getting, sure here, I believe I get negative 75.8 newtons here, and then positive 368.8 newtons here. So let's check that. It's highly possible I missed something. Okay, 76 and 370. So there might have been like a, what is the magnitude of this, I imagine, because if it's pointing that way for this force on this one, then it has to be that its horizontal component is negative if we're calling to the right positives. There probably was a magnitude thing here. 76 and 370. And yeah, if I round, that's 76 and 370. Okay, so that one, a little bit of a mistake at the beginning there, but is that one okay? Ah, okay. All right, others. So this one's a little interesting because it seems like you'd have to do some calculation, but it's more about just knowing how vectors add together. So maybe give this one a try. And it is a conceptual question in a sense, but there is an answer you'd put here. So give that one a try. So let's see if that'll work for me. So poll is just yes, it is possible, or no, it is not possible to um, to have a net force of 0 on that charge, positive Q or capital Q, excuse me. So is it possible? If so, say yes. If not, say no. Okay, so we're leaning more towards yes, it is possible to have a 0 net force there. So let's draw some things in here. We said could be positive or negative. I'm just going to choose one, just see what happens. So say this is positive first, then it's going to be repelled by B. It's going to feel a force this way. Oh, can't draw a straight line to save my life today. It's going to be pushed that way. And then C is going to push on it the other way. So what can we say about those two forces? They cancel out. We've got the same charge here, and then both of these are a positive Q, whatever Q is. And so the force on this large Q charge due to this charge is exactly equal in magnitude to the force on it due to this one, and they're in opposite directions. So they cancel out. Okay, so you are always left with, regardless of the size of this charge, these forces canceling out, but still this one, if it's Q is positive, still repelling it. So it's still going to feel that force downward. If we had negative charge for Q, then nothing really changes. It's just that now it's attracted by this one over here. So instead of this vector, we have this one pointing towards, and then it's attracted towards C. But those still cancel each other out, and then we're left with it being attracted by the one up there. So you're always left with the force due to the charge at A, and there's nothing to balance it. What you would need, if you want it to have the same strength, Q, is to make the figure itself completely symmetric. Put another charge here, Q, and have those lengths still both be A. And then if we have a positive charge here for a capital Q, that will balance out this one down here so that they cancel. Or if we have negative attracted towards this one down here, that will balance out this one. And then you can have a net force of 0. But typically for things like this, unless you change the values of these charges so that they can balance, you are not going to have cancellation. So it is potentially possible if the magnitude of the charges for B and C are different, because then we feel a net force one way or the other. And we could have, well, actually we still couldn't in that case, because we'd have a net force pointing one direction horizontal. This one's purely vertical. You can't add a horizontal and vertical force to get 0 net force because they're perpendicular to each other. They can't cancel out because they're in opposite directions. So really, even in that case, it wouldn't work well. So triangles, usually you're not going to have a net force of 0 unless maybe you have something right at the center. Okay, does that make sense to everyone? Because I can seeing it being 0 net force just because we think, well, there's got to be some way. But if we just kind of go through the motions of looking at the forces, we see it's not possible. Okay, I'll take that as a yes, I guess, that it makes sense. Are there other questions? Right, if there's not questions, I'm happy to cut it off wherever. So let's see. This is kind of your call to, if there's questions, now's the time, because we'll cut it off otherwise. But I'm happy to keep going over whatever. I don't think there's any other exam details I want to give. Just be working on your equation sheets, or cheat sheets is really what I should call it, because one, you're given a lot of the equations, and two, it's so you can put whatever you want on there. Okay. So yes, exam covers up to capacitance, but it's chapter 18 and 19. So the entirety of both chapters, except at the end of chapter 19, we did not go into any detail on biomedical applications of potential differences, which is section 19.6, I think, the very last section of chapter 19. That's not on there. We just kind of gave a quick run over of that bit. But up through section 19.5, I guess I should say, of chapter 19 is fair game for the exam. Well, all right. If no other questions, yes, yeah, the whole class period. So 55 minutes. And I'm usually not too bothered if, it takes up until whenever the next class needs to come in. But as soon as people start coming in for the next class after you guys, I'll probably be looking at you like, all right, let's get the show on the road so they can get their next class started. But knowing which equations to use for a particular problem. So I come up here. We can kind of go from general to specific. And usually that's the way you want to go when you're thinking about answering stuff. Is the most general way always works in the sense of if you're given the information, it should apply. So for electric fields, that one is the definition of the electric field. It's the force felt by a positive test charge. Same with potential, that's the most general. And those are our, well, and then Newton's laws just apply to anything you would care to look at. And we'll say conservation of energy. And okay, this one too. So these are like general, they work no matter what type of situation you're looking at. And they don't have a lot of these subscripts that we have for other things. So like this one, it's Coulomb's law, it applies to point charges. And if you use it on a capacitor, you're going to get the wrong answer. Similarly, this is the electric field for a capacitor. If you use it on point charges, you're going to get the wrong answer. So you always want to start with the most general, but then if you're told it's a point charge, it says specifically in there, a point charge or like a concentration of charge, a small region of charge, there's sometimes different wordings to try and trip you up. But if it's something like that, then you can jump to, oh, well, the potential of a point charge is kq over r. The electric field is kq over r squared. The force between 2 point charges is Coulomb's law. But you only can do that once you're told this is something about point charges. Similarly, capacitors, you can use this equation, which is a more specific one than it's just charge times the potential difference, but only if you're dealing with the potential energy stored in a capacitor. So we could kind of largely break what we've done into, you're not told enough information to know it's a capacitor or point charges. You are told enough to know it's a point charge, or you're told enough to know it's something with a capacitor. And for things like you've got a point charge in a capacitor, that is still not either case, right? It's not just a capacitor, it's not just point charges. So you still have to resort back to, well, all I know is the electric field here for the capacitor, and the point charge has that value Q naught. I know the force on that charge is Q naught E. Whatever, so E I do know something about since it's capacitor's electric field. But I don't know the force right off hand. So that's what we would have to do, for instance, for this problem, finding the force on this charge. We just apply our definition of electric field. Then we can remember that for the capacitor, it's that charge density or just charge per area over epsilon naught. So I guess my advice is think about, are you looking at point charges? Are you looking at capacitors? Are you looking at something that you don't have enough information to know that it's either? And that should give an idea of which equations apply. Okay. If no other questions, we'll go ahead and finish off here. So I'll have this uploaded on YouTube within, sometimes it's quick, sometimes several hours of it just sitting there not doing anything. So I can't really say exactly when it will be up, but by the end of today, it will be up. And I will link that on Wiley in the same module as all the other exam review stuff. And thanks to Haley in your class, she's going to do timestamps to know when we went over different things, and that makes it a little bit easier to jump around for reviewing things. So thank Haley for that. All right, well, I will see you all on Monday. Best of luck with the exam. There will be donuts as a peace offering, so that even if the exam is rough, maybe you at least got a donut at the end of it. It's going to take longer for me to grade the exams than last semester for those of you who had it with me, because of that different way of grading things that I mentioned. And just that is all these other things I have going on that I didn't last semester. So it will be a little bit getting the exams graded. I'll just put that out there now so we know. Okay, well, thanks all who could attend for attending, and that's all I have. So I'll see you on Monday. All right, thank you.